Today's lesson is a continuation of section 7.2, solving linear systems by substitution. In this second part of this section, I'm just going to go through a few special case problems or some interesting things we should be aware of when we're solving systems using substitution. I'm going to start off with this example here that I've got for number 1. And again, if you're still having some trouble on solving with substitutions or not sure what to do, I would watch the first part of this lesson, but this second part can help with a few special cases or other things that may happen. So looking at this system, again, I'm going to solve this with substitution. It's set up very well for me to do so. It's already solved for a variable, y equals, and then this expression over here for the first equation in the system. So what I can do is I can substitute 2x minus 5 in for y into the second equation. I'm going to rewrite it and see what it looks like now. I'm going to have 3x minus, and then in parentheses, 2x minus 5. That expression equals 10. Now notice how when I substitute things from one equation into another, I always use parentheses, and here's kind of the key why. Sometimes when you substitute something in, you're going to have to distribute. Sometimes you might just have to add or subtract something, but it still will be important for you to have parentheses around it. Like in this particular example, it says 3x minus, and then whatever I have in parentheses here. So what I have to think of, there's two ways that I talk about it sometimes. I have to think that I'm going to subtract each of those things in that parentheses, each of those terms in that expression that's inside the parenthesis. That's one way I could think about it. So I could say, if I'm going to rewrite this, it's almost like distributing that subtraction sign to each of these numbers, and say I'm going to subtract them in this problem. I could say 3x minus 2x. And then again, that subtraction also has to go to the second number in the term, as I'm showing here with this arrow. I also have to subtract negative 5 is what that really turns into. And so when I chop, I'm going to change that to plus 5 is really what's going to happen in this case. So notice how, because there was a subtraction sign in front of what I substituted in, I still have to take that into account and think that I'm subtracting everything in that expression. Here's another way to think about it as well. Again, this is something you definitely will run into from time to time when you're doing these problems. So this is something I definitely want you to learn and know how to deal with. I'm going to substitute that expression in for y. So it's going to be 3x minus, well then that expression, I'm still going to use parentheses, 2x minus 5 equals 10. Well then, again, another way to think about this is usually there is some number, maybe some coefficient in front of the variable that I would have to distribute. Well, if I have just y sitting there by itself, remember there is a coefficient on y. There is a number in front. It really is like a 1. And so this is like negative 1y I could think of. So then also in this next line, I'm just going to back everything up a little bit so I can sneak it in there. But I could also think of this like 3x minus 1 times the things that I have in parentheses. And if I chop dashes just to make it a little more clear, I can think of this like a negative 1 is what I'm going to distribute to each of these terms. And if that's an easier way for you to think about or to understand that I have to really distribute that negative to both terms, then think of it that way. So what do I get when I distribute that negative? 3x minus 2x, just like we had before. And then again, this is going to be plus 5, because I'm going to take negative 1 times negative 5, so it's going to give me plus 5 equals 10. Once I get to that next step, now again, it's just like solving a multi-step equation. I can combine 3x and 2x, and I can get x plus 5 equals 10. Subtract 5 from each side, and I'm going to get x equals 5 in this case. Again, the problem's not over. Just a reminder from the first part of the lesson. The problem's not over. Now I've just got one of the coordinates. I've got one of my coordinates for my ordered pair. I've got the x, so that's 5. And now I'm going to go about and try to find out what y is. Again, you can plug it into either equation. It won't matter. But it looks like the top one might be a little easier. All I have to do is take 2 times 5, which is 10, and minus 5 from that, so I'm getting y equals 5 for my y coordinate as well. Again, just showing the picture of what this really looks like. If I decided to do this, solve this linear system by graphing, what this solution is saying is that this is the point where those two lines, the graphs of those two equations, should cross at 5, 5. So where's that point? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here's the point. 5, 5. Excuse me. Now I'm going to graph the top equation, y equals 2x minus 5. It has a y-intercept of negative 5, and then I'm going to go up 2 over 1, up 2 over 1. Looks like it goes right through my 0.55, so that's a good indicator that maybe this is the right line. And for the second equation, I'm going to use intercepts method. So recall that method as well. I could change it around and use slope-intercept form if I want, but I'm going to use intercepts method. So it'll look like my y-intercept will be negative 10, which would be down here, 0, negative 10. And my x-intercept will be about 3 1/3, so over 3 and about 1/3. So it's going to be a little tougher, but I bet still you can get the idea here. That those lines are, yep, still going to cross at about the 0.55. So I still did a pretty good job. And again, that should make sense when I substituted. Right? When I did substitution, I came up with the same answer. So that should always happen. Whether you graph a linear system or you solve a linear system, you should still get that same point wherever they cross. In this case, 5, 5. Here's another problem I'd like to talk about that we can solve with substitution, a linear system. But again, something kind of funny is going to happen as we're solving this one, as you're about to find out. But let's first solve it just like we would any other problem, because I want to show you that even when we have some special cases or special situations when we're solving a problem, if you still go about the normal steps, you'll run into it. You don't have to realize like right off the bat, ooh, this is a special case. No, you'll run into it as you do the problem. So don't feel like you have to do anything special right away. Let's just first start off doing the problem as we would. Well, looking at this problem, first thing I might realize is, well, I want to set it up for substitution because it's not yet. So what I could do is let's take this top equation. To have this problem set up for substitution, I need one of those equations to be solved for one of the variables. This top one I think I could solve easily just by subtracting 3x from both sides. If I do that, now I'm going to rewrite this one as y equals, well, negative 3x plus 12. And I can go from here. Now I can solve this equation. I can solve this linear system by using substitution. I have y equals negative 3x plus 12. So again, I have y equals and then some expression. So I can take and plug this stuff in for y in the other equation. And when I do that, this should help me start solving it. So let's see what happens here. I'm going to have 9x plus 3 times that expression that I'm now plugging in for y, or substituting in for y, negative 3x plus 12. And that equals, in this case, 0. Okay, so far so good. Now what I do next is I'd start distributing and trying to collect like terms and try to solve this for x. So let's see here. If I distribute that 3 to both those terms inside there, I'll get 9x, and then 3 times negative 3x will give me, well, this will be minus 9x, and then plus 36 equals 0. Okay. Well, so far so good still. But now when I try to collect like terms, notice what happens here. I'm going to have 9x minus 9x, which is going to give me, well, no more x's. So those are going to cancel out. So I'll get 36 on this side, but 36 is not equal to 0. So I'd put a slash to this equal sign. That's not a true statement. So as I'll ask the students in class, I'll say, well, what do you think the case is in this situation? If all of a sudden my variables cancel out and I have something that's not true. We've actually seen something like this before when we've solved equations in the past. And hopefully I'm hoping students that will come about to the conclusion that we've seen this usually when we're talking about a no solutions case. And that's exactly what we have here. There's no solution for this linear system. Well, what does that mean? Well, usually when we solve a linear system, we can find that one point where the two lines cross. Well, if we're saying that there's no solution, we're saying there is no point where the two lines will intersect, or lines will cross. So what must be happening here is these two lines, I'm guessing, okay, and as we learn, these two lines must be parallel because they don't cross ever, so there's no possible solution. Let's graph them just to show that this is what's really happening. So I'm going to go back to those original equations. And I think I am going to put them both in slope-intercept form just to also show another way we can see this. So this first one, as I did before, I'll do it one more time. I'll subtract 3x from both sides. And I'll get y equals negative 3x plus 12. And even though I've got 12 as my y-intercept and it kind of goes off my grid, I can still imagine it's about right here. And then I would go down 3, so 11, 9, 11, 10, 9, and then go over 1. So I'd be about here, down 3 over 1 again. So I can still use my slope, even though I go a little bit off the grid. That's okay. I can imagine the line being like this. I can draw a straight one. Something like that. I'm going to do the same thing for the second equation. I'm going to solve this one and put it in slope-intercept form. So I would subtract 9x from both sides, and that would give me 3y equals negative 9x. And if I divide both sides by 3, I get y equals negative 3x. So here's one of my equations in my system, and here's the other one. I've changed them both a little bit, but really they're still the same equation. This one starts at the origin and also has a slope of negative 3 over 1. So here would be this line. And again, if I draw a good one, oh, that wasn't as good. I'm going to try to draw nice and straight so you can see, but I think you're starting to get the idea. This line as well, since it has also the same slope, remember what do we know about parallel lines? They have the same slope. So if I was even just solving these equations for y, and notice that they're in slope-intercept form, that they have the exact same slope, that also tells me they're going to be parallel. So this is what happens when we have the no solution case, when we're using substitution. They're solving a linear system with substitution. What will happen is we'll get down to a situation like this, where all of a sudden the variables have dropped out, and we have something that's not equal. 36 does not equal 0, so this is the no solution case. And that tells us the two lines that we're talking about must be parallel to each other because they never intersect. I'm going to show us one more case in this lesson. And some of you, maybe if you kind of know stuff from the previous lessons, you've been paying attention, you might even know what case this is going to be as well. We just talked about the case where there's no solutions in a linear system. Well, I'm going to solve this last one here with substitution. But I'll show you one other thing that can come up when we're solving these as well. This one's already set up nice for substitution. It's got y equals, and then it's got this expression on the right side of the equation. So I can substitute right now and plug 2x minus 4 in for y in my second equation of the system. Well, then what I'm going to do, oops, and actually I see I have two y's in here. I just kind of noticed that mistake myself. Okay, what I'm going to do is I'm going to change that equation really quickly. That one should be 6x. So there we go. That's what I was going for. And that'll also help with the substitution to actually get it right, so that's probably a good thing. Y equals, okay, again, 2x minus 4, so y equals this expression, so I'm going to substitute in for y now, and it'll help that I actually have an x in there as well. I'm substituted in for this spot in for y. So now I have 3 times, well, this expression, 2 minus 4, or 2x minus 4, minus 6x equals negative 12. So I've taken that first equation and used substitution to put some of it in for the second, into the second equation. And now I can solve and find out what x is. Again, if you're looking for one of these special cases, you don't have to know that anything's going on yet. You can just keep using your normal steps and solving like we usually do. 3 times 2x gives me 6x. 3 times 4 gives me 12, so 6x minus 12. Minus 6x equals, well, negative 12. Well, right now at this point, you already might start to notice that something is going on here, though, with this problem. If I try to collect like terms, here's 6x, and it says to subtract 6x when I combine those. Well, what happens again in this case is my x's cancel out, just like the previous case. But now I get something different for this situation, this problem. All I'm left with is negative 12 equals negative 12. Now, unlike the previous case, where we talked about how 36 was not equal to 0, so we put a slash through, and that's the no solution case. In this situation, negative 12 is equal to negative 12. That is true. So what do we put in this particular case? Well, solving with substitution, this case is actually the infinite. We say there's an infinite amount of answers, or amount of solutions. There's an infinite amount of solutions. What does this look like on the graph? Well, what happens in this case, if I look at the two equations, I'm going to graph them. But something maybe you might even notice just by looking at the numbers now, there's a connection between these two equations. But let's graph them here, and you can see it on here as well. Y equals 2x minus 4. I'd go down 4 spots to the y-intercept, up 2 over 1, up 2 over 1, up 2 over 1, and I can make my line. There's the graph of the first equation. For the second one, I'm going to use intercepts method, even though this one looks a little different, though you'll notice something interesting. If I use intercepts method, I see that my y-intercept will be -4, and my x-intercept will be +2. What do you know? Those are 2 points that I already used. And using the slope, I can actually find out that this line will have the same slope as the blue one. And if I graph it, it's the exact same line. So this is why we say there's an infinite amount of solutions. Not that every single point on the graph is a solution, but any single point that falls on this line is a solution. So there's an infinite amount of them because remember, this line goes on and on forever. So I could pick out any point, a point here, or a point here, or a point here, or somewhere off in the future. If these lines keep extending, I could pick any point and keep finding more and more solutions because any point that would work on either of these two lines would be a solution. So since the line is since these two equations represent the exact same line of solutions. So this last special case is the case where there's an infinite amount of solutions, something else we could run into when we're solving using substitution.